Hello, good morning, students. Let us continue our current topic alcohols, phenols, and ethers. Okay, we have seen physical properties of alcohols, phenols, and ethers. Now, let us see reactions of alcohols and phenols. But here, these reactions based on cleavage of OH bonds. Hmm? See, first point acidity of alcohols and phenols. The first reaction with metals. So reactions of alcohols and phenols with metals. Alcohols and phenol react with active metals like sodium, potassium, and aluminum to give corresponding alkoxides and phenoxides along with liberation of hydrogen. Okay, see, two molecules of alcohol ROH plus 2 sodium, it gives sodium alkoxide plus liberation of this hydrogen. If aluminum is taken as active metal and here tertiary butyl alcohol, it's 6 molecules to aluminum, it gives aluminum tertiary butoxide. So this is tertiary butyl group and this is oxide. So aluminum tertiary butoxide with liberation of hydrogen gas. Okay. Now reaction of phenol with sodium. Two molecules of phenol reacts with sodium. It gives two molecules of sodium phenoxide with liberation of hydrogen gas. Acidity of alcohols. The polar nature of OH bring the acidic character in alcohols. We know that OH bond is polar in nature because oxygen is more electronegative than hydrogen. So the shared electron pair in this bond, OH bond, is more attracted towards oxygen side. Hence, oxygen get partial negative charge and hydrogen get partial positive charge. Okay, so OH bond has polar nature. If the electron releasing group increases, the electron density on oxygen, which decreases the polarity of OH bond. Polarity of OH bond and hence decreases the acid strength. See here in this example, the acid strength of alcohol decreases in following order. This is primary alcohol RCH2OH, this is secondary alcohol R2CHOH, and this is tertiary alcohol R3COH. So here alkyl groups, these are electron releasing group or electron donating group. Because of this, electron density on oxygen increases. Electron density on oxygen in each alcohol increases, by which the polarity of OH bond become less or decreases, and hence acid strength of it also decreases. Acid strength of that alcohol also decreases. See here, this is primary alcohol, this is secondary alcohol, and this is tertiary alcohol. Alcohols are weaker acids than water. Here, the strength of acidity of any organic compound depends on ease of releasing H plus ions. So, definition of acid according to Arrhenius theory, if it is dissolved in water or taken in aqueous solution, it loses H plus ion, then it behaves as acid. So here, strength of acidity of any organic compound depends on ease of releasing H plus ions, and latter depends upon the stability of conjugate base that forms. Any factor that stabilizes the conjugate base of acid increases its acidity. So here, in this case, primary alcohols are more acidic than secondary than tertiary. Again, the next point is alcohol act as Bronsted bases due to presence of unshared electron pairs on oxygen. So oxygen has unshared unused electron pair, so they can behave like as Bronsted base. Acidity of phenols. Phenols are more acidic than alcohol and water. In phenol, the hydroxyl group is attached directly to sp2 hybridized carbon of benzene ring, which act as electron withdrawing group. Due to this, the charge distribution in phenol molecule causes the oxygen of OH group to be positive. See here, this is phenol. This lone pair of electron is withdrawn. It is pulled towards this electron withdrawing benzene. Benzene is electron withdrawing group. So this electron of oxygen is withdrawn, and in this way it goes here, negative charge shifted over here. In this way, negative charge again goes here, then at para position. Again here at ortho position. In this way, these are resonating structures. Okay, the ionization of alcohol and phenol take place, producing alkoxides and phenoxides. ROH, when it loses H plus ion, it gives alkoxide RO minus. When from phenol H plus ion is removed, then it forms phenoxide ion. So in this alkoxide ion, the negative charge is localized on oxygen, but in phenoxide, in phenoxide, the charge, the negative charge is delocalized. This delocalization of negative charge make phenoxide ion more stable and favors the ionization of phenol. So in this way, negative charge in this way, so delocalization of negative charge favors the ionization of phenol. Okay. Esterification. Esters are formed when alcohols and phenol react with carboxylic acids, acid chlorides, and acid anhydrides. The reactions are given below. So here, simply general reactions of alcohol or phenols are mentioned. AROH or ROH, that is phenol or alcohol. So when phenol or alcohol react with carboxylic acid in presence of H plus ions, it forms ester, corresponding ester of phenol or corresponding ester of alkyl group, corresponding ester of aryl group or alkyl group. Okay. When AROH or ROH, that is alcohol or phenol, reacts with acid anhydride, again ester formation take place. That is ester of aryl group or alkyl group along with corresponding carboxylic acid. Okay. If alcohol or phenol reacts with acid chloride R dash COCl in presence of pyridine, pyridine is organic base, then ester formation take place. So this ester formation take place from alcohol and phenol when they react with carboxylic acid or with acid anhydride or with acid chloride. Corresponding ester formation take place. So this is esterification. This is esterification. Reactions involving cleavage of CO bond in alcohols. Only alcohols undergo this type of reaction which involves cleavage of CO bond. In phenols, this type of reaction takes place only with zinc. First, reaction with hydrogen halide. ROH plus HX in presence of ZnCl2, it gives alkyl halide plus H2O. Reaction with phosphorus trihalides. 3 molecules of alcohol plus PCl3 or PX3, in general PX3, it gives 3RX, 3 molecules of alkyl halide plus H3PO3, where X is equal to Cl, Br. Okay. Dehydration. Dehydration means removal of water molecule. Dehydration of ethanol is given as below: C2H5OH, CH3CH2OH, CH3CH2OH in presence of dehydrating agent like H2SO4, C2H5OH, H2SO4 at 443 Kelvin. Now here CH3 CH2OH. So let us see CH2 CH2, let me write complete OH. So it takes too much time to write by this pen. So I prefer to explain just by laser pointer. So this is C2H5OH, CH3, CH2OH. So what happens here? This hydrogen goes here, or see, this water molecule get removed, and here carbon carbon double bond formation take place. CH2 double bond CH2 plus H2O, removal of water molecule. Okay, in this way reaction take place. Dehydration of secondary and tertiary alcohol take place under mild conditions, and reaction is as given below. CH3, CHOH, CH3. Now here from this carbon, hydrogen. So HOH is removed as water molecule, and carbon carbon double bond formation take place here. So this way. But here the condition becomes mild, 85% H3PO4, and temperature is also 440 Kelvin. If tertiary alcohol is taken, H3PO4 is 20% and low temperature, that is 358 Kelvin. Now here H, CH2, H, that is CH3. So this water molecule is lost, dehydrated by this acid. So carbon carbon double bond formation take place along with liberation of elimination of water. Here the order of dehydration of alcohols is shown as tertiary alcohols greater than secondary alcohols greater than primary alcohols. Okay. Oxidation. Primary alcohols, next reaction is oxidation. Primary alcohol oxidize to aldehydes, which on further oxidize and gives carboxylic acid, which depends on the type of oxidizing agent used. See, this is primary alcohol. On oxidation, it gives aldehyde, which on further oxidation gives carboxylic acid. Let us see actual this change take place. CH2OH, this primary alcoholic functional group, is oxidized to CHO group, that is aldehydic functional group, and this aldehydes on further oxidation gives this carboxylic acid group. See, primary alcohols on oxidation gives aldehydes, and aldehydes on further oxidation gives carboxylic acid. Okay, an oxidizing agent CrO3 can be used for isolating aldehydes. If only up to aldehyde we want to prepare only aldehyde by this oxidation, then use CrO3. So this is the reaction. Primary alcohol in presence of oxidizing agent chromic acid, it gives corresponding aldehyde. Pyridinium chlorochromate, PCC, can be used an oxidizing agent to get aldehyde from primary alcohols. CH3CH double bond CH CH2OH. Pyridinium chlorochromate this typical or specific oxidizing agent which oxidizes only this CH2OH group to CHO group. This part remains unreacted or it remains as it is. Carbon carbon double bond, it does not undergo oxidation. On oxidizing on oxidation, secondary alcohols gives ketones using CrO3 as an oxidizing agent. Now these are secondary alcohols. Secondary alcohols, so this is secondary alcoholic functional group CHOH. This group undergo oxidation to form this C double bond O. C double bond O, that is ketonic group. So remember here, primary alcohols on oxidation gives aldehydes and secondary alcohols on oxidation gives ketones. But for tertiary alcohols are stable for oxidation. But if on strong and destructive oxidation of these tertiary alcohols is carried out, then they gives corresponding ketones with one carbon less than the initial alcohol. Okay. Dehydrogenation. Now D means removed and hydrogen means here in this reaction hydrogen H2 is removed. So this is primary alcohol. Primary alcohol when heated in presence of copper at very high temperature 573 Kelvin. See here total 3 hydrogens, 2 and this is 1, 3 hydrogens. So H2 is removed, eliminated, and here only one hydrogen is left. So RCHO, that is primary alcohol on dehydrogenation gives aldehydes. Same case, this is secondary alcohol RCHOH R dash. Now here two hydrogens. So 573 Kelvin in presence of copper, it gives this carbonyl group. This is carbonyl group. Okay, means no hydrogens. So hydrogenation, dehydrogenation. Here one hydrogen from this carbon and one hydrogen from OH group is get eliminated and it forms carbon double bond CH2 group. Okay, so here this is dehydrogenation. Halogenation of phenol. Phenol reacts with, let me take a laser pointer. Phenol reacts with aqueous solution of bromine to give 2,4,6 tribromophenol. Chlorine reacts in same way, bromine or chlorine. But here in this bromination, there are two conditions. Phenol reacts with bromine in presence of water as a solvent. This is water. And Phenol reacts with bromine in presence of carbon disulfide as a solvent. So in two different solvents, the reactions of phenol with bromine or bromination of phenol take place in different manner. So phenol when react with bromine in presence of water or bromine water, it gives 2,4,6 tribromophenol. When phenol reacts with bromine in presence of carbon disulfide at low temperature, it gives a mixture of orthobromophenol, and this is parabromophenol. See, both products are different as the solvent condition changes. Here water as solvent and here carbon disulfide as a solvent. Now next, nitration of phenol. Nitration means to introduce nitro group in the benzene ring. Phenol reacts with dilute nitric acid at low temperature to give mixture of ortho and paranitrophenol. See this reaction. Phenol plus nitric acid HNO3. Nitric acid HNO3. For our convenience, we have written it as HONO2, HNO3, HNO3. Okay, we have written it OHNO2, HNO3. Okay, nitric acid, this is dilute. Acid is dilute. So here two different conditions. Phenol reacts with dilute nitric acid to form ortho and paranitrophenol, mixture of ortho and paranitrophenol. But here in this second reaction, phenol reacts with concentrated concentrated nitric acid to form 2,4,6 trinitrophenol, or it is also called as picric acid. It is called as picric acid. See, phenol plus concentrated HNO3 in presence of nitrating agent H2SO4 in presence of concentrated H2SO4, it gives 2, 4, 6 trinitrophenol, or it is also called as picric acid. It is also called as picric acid. Means for nitration of phenol, these two different conditions. So dilute nitric acid and concentrated nitric acid. This is concentrated, dilute and concentrated. With dilute nitric acid, it gives a mixture of ortho and paranitrophenol. With concentrated nitric acid, it gives 2,4,6 trinitrophenol. Okay, let us go ahead and sulfonation. Sulfonation of phenol. To introduce SO3H group in benzene ring. This is sulfonation. Phenol reacts with concentrated sulfuric acid at room temperature to give orthophenol sulfonic acid, and at 373 Kelvin paraphenol sulfonic acid. See here, phenol plus H2SO4. So we have written this as OHSO3H. Low temperature, OHSO3H, high temperature. So this is normal at room temperature, and this is at 100 degree Celsius, near about 100 degree Celsius. The reaction takes place in different ways. At low temperature, the product is orthophenol sulfonic acid, and at high temperature, the product is paraphenol sulfonic acid. Okay, see these three reactions. Halogenation means bromination. It has two conditions: bromination in presence of water and bromination in presence of CS2. It gives two different products: 2,4,6 tribromophenol, and for second it gives orthobromo and parabromophenol. Let me find here our cursor. Yes, now this is parabromophenol is the major product. It is major product because both Br and OH, they are far away from each other, so this is more stable than this, because here OH OH and Br, they are close to each other, and because of steric hindrance their stability is weak. Nitration, this nitration take place with two different conditions, that is with dilute nitric acid and with concentrated nitric acid. So with dilute nitric acid, it gives mixture of ortho and paranitrophenol. With concentrated nitric acid, it gives picric acid. Sulfonation, it has also two conditions: at low temperature and at high temperature. At low temperature, orthophenol sulfonic acid formation take place, and at high temperature, paraphenol sulfonic acid formation take place. Okay. Rimmer-Timon reaction. When phenol is treated with chloroform in aqueous sodium hydroxide followed by hydrolysis with acid, salicylaldehyde is formed. This reaction is known as Rimmer-Timon reaction. So this is phenol reacts with chloroform CHCl3 in presence of aqueous NaOH. It gives this intermediate compound, which on further reaction with NaOH and further hydrolysis, it gives salicylaldehyde. If carbon tetrachloride is used in place of chloroform, salicylic acid formation take place. This is Rimmer-Timon reaction. Now oxidation of phenol. Phenol on oxidation with chromic anhydride or sodium dichromate Na2Cr2O7 in presence of H2SO4, it gives parabenzoquinone. Phenol reacts with CrO3 or sodium dichromate in presence of H2SO4. Parabenzoquinone formation take place. Phenol oxidizes slowly, giving dark colored mixture in presence of air. Catalytic hydrogenation. Catalytic hydrogenation of phenol. Phenol on catalytic hydrogenation, it gives cyclohexanol. It gives cyclohexanol. In this reaction, a mixture of vapors of phenol and hydrogen is passed over nickel catalyst at 433 Kelvin. So this is phenol and this is 3H2. So all these three hydrogens get added across this carbon-carbon double bond. So double bond changes to single bond. This double bond changes to single bond, and this double bond changes to single bond. So all these three alternate double bonds here, three to the six hydrogens get added across these double bonds, and they becomes CH2, single bond 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 CHOH. Got it? So this is cyclohexanol. Reduction of phenol. Phenol is reduced to benzene on heating with zinc dust. So phenol, when heated with zinc, it gives benzene plus oxide of zinc. Okay, phenol when treated with or heated with zinc, metallic zinc, it produces benzene. About this ethers, we will see in next lecture. So up to this, we have seen the chemical reactions of alcohols and phenols. Okay, this topic ethers we will see in the next lecture. Okay, thank you.